Imagine a universe where space is not a rigid stage, but a flexible, responsive fabric. This is not science fiction, but the reality revealed by Albert Einstein's revolutionary theory of relativity. He called this fabric spacetime. Spacetime is the very essence of our universe, a dynamic entity that bends and curves under the influence of mass and energy. Einstein's theory forever changed our understanding of gravity and the cosmos. It unveiled a universe stranger and more wondrous than we ever imagined, where black holes warp spacetime to its limits and time itself flows at different rates depending on your location. This is our universe, a cosmic dance choreographed by the elegant interplay of mass, energy, and spacetime. We experience the world in three dimensions: length, width, and height. These dimensions define our spatial awareness, allowing us to pinpoint locations and navigate our surroundings. However, Einstein revealed a hidden truth. Time is not a separate entity but an integral part of this cosmic fabric forming the fourth dimension. This concept, known as space-time, revolutionized our perception of the universe. It's not just things exist, but also they exist that matters in this grand cosmic scheme. Space-time is the stage on which the events of the universe unfold, a four-dimensional tapestry woven from the threads of space and time. Imagine a vast, perfectly flat rubber sheet. This sheet represents space-time in its purest form, devoid of any matter or energy. In this pristine state, space-time is flat, and objects travel along straight, predictable paths. Now, introduce a bowling ball onto the sheet. The ball, representing a massive object like a star or planet, creates a dip in the fabric. This curvature is what we perceive as gravity. Space-time is no longer flat but warped, its geometry altered by the presence of mass. This simple analogy illustrates a profound concept. Gravity is not a force acting at a distance but a consequence of space-time's curvature. The more massive the object, the greater the curvature it induces, and the stronger its gravitational pull on surrounding objects. Sir Isaac Newton described gravity as a force of attraction between objects. This force, he proposed, acted instantaneously across vast distances, keeping planets in orbit and apples falling to the ground. While groundbreaking for its time, Newton's theory could not fully explain certain astronomical observations, such as the slight wobble in Mercury's orbit. Einstein's theory of general relativity provided a more complete and elegant explanation. He showed that gravity is not a force but a consequence of space-time's curvature caused by mass and energy. Objects don't attract each other in the traditional sense. Instead, they follow the curves in space-time created by massive objects, much like marbles rolling around the dip made by a bowling ball on a rubber sheet. This revolutionary idea redefined our understanding of the universe. Gravity was no longer an invisible force acting at a distance, but an inherent property of space-time itself. Einstein's theory provided a more accurate and comprehensive framework for understanding the cosmos, paving the way for modern astrophysics and cosmology. In the grand cosmic ballet, mass and spacetime are the principal dancers, locked in an intricate and inseparable embrace. Mass tells spacetime how to curve, and spacetime in turn tells mass how to move. This elegant interplay governs the motion of planets, stars, and even light itself. Imagine a star, its immense mass warping the fabric of spacetime around it. Planets orbiting the star are not pulled by an invisible force, but rather follow the curvature of spacetime, much like marbles rolling around a funnel. The greater the mass of the star, the steeper the curvature, and the faster the planets must orbit to maintain their paths. This delicate balance between mass and spacetime shapes the cosmos into the structures we observe. Galaxies spiraling through the universe, stars clustered in vast systems, and planets orbiting their parent stars in intricate cosmic dances. Cosmic curiosities, black holes, and the bending of light. In this chapter, we delve into the mysterious and awe-inspiring phenomena that challenge our understanding of the universe. The bending of spacetime gives rise to some of the most fascinating and perplexing phenomena in the universe, including black holes and gravitational lensing. These cosmic wonders stretch the limits of our imagination and scientific knowledge. Black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape their grasp. They act as cosmic vacuum cleaners, pulling in everything that comes too close. These cosmic behemoths form when massive stars collapse at the end of their life cycle. their immense mass compressed into an infinitesimally small point called a singularity. This process is both violent and spectacular, often resulting in a supernova explosion. The singularity's gravitational pull is so intense that it creates a region of spacetime from which nothing can return, hence the name black hole. The boundary of this region is known as the event horizon. Gravitational lensing is another intriguing consequence of spacetime curvature. This phenomenon allows us to see the universe in a completely different light, quite literally. As light travels through the universe, it follows the curves in spacetime created by massive objects like galaxies and galaxy clusters. This bending of light can reveal hidden details about the cosmos. This can cause light from distant objects to bend around these massive structures, creating distorted or multiple images of the background object. These visual distortions are like nature's magnifying glass. These lensing effects, predicted by Einstein's theory, provide compelling evidence for the curvature of spacetime and allow astronomers to study extremely distant objects in the universe that would otherwise be too faint to observe. Through these cosmic lenses, we gain a deeper understanding of the vast and mysterious universe. Time's twisted path. Dilation and its implications. Time, once thought to be an unwavering constant, is also subject to the warping effects of spacetime. This revelation has transformed our understanding of the universe. Einstein's theory revealed that time flows at different rates depending on the strength of the gravitational field. This groundbreaking idea challenged the very fabric of physics. This phenomenon, known as time dilation, has profound implications for our understanding of the universe and even our everyday lives. It affects how we perceive time and space. In regions of strong gravity, such as near massive objects, time slows down relative to regions of weaker gravity. This effect is more pronounced the closer you get to these massive bodies. This means that a clock placed near a black hole would tick slower than an identical clock on Earth. The difference, though subtle, is measurable and significant. While this difference in time is minuscule on Earth, it becomes increasingly significant near extremely massive objects. The closer you are to a massive object, the slower time moves. Time dilation is not just a theoretical curiosity, it has practical applications in technologies like GPS satellites. These systems rely on precise time measurements. These satellites, orbiting Earth at high altitudes, experience a slightly weaker gravitational field than clocks on the ground. This difference must be accounted for. To ensure accurate positioning, GPS systems must account for this time difference, demonstrating the tangible impact of spacetime curvature on our technological advancements. Without these adjustments, our navigation systems would be far less accurate. A universe in motion, expansion, dark energy, and wormholes. Spacetime is not a static backdrop, but a dynamic entity that evolves over time. Observations have shown that our universe is expanding, with galaxies moving away from each other at an accelerating rate. This expansion is driven by a mysterious force called dark energy, which makes up roughly 68% of the universe's total energy density. The nature of dark energy and its relationship to spacetime is one of the biggest mysteries in modern cosmology. Some theories suggest that dark energy is a property of spacetime itself, a sort of anti-gravity that pushes spacetime apart, driving the universe's accelerated expansion. Another intriguing consequence of spacetime curvature is the theoretical possibility of wormholes. These hypothetical tunnels through spacetime could connect distant points in the universe, potentially allowing for faster-than-light travel. While the existence of wormholes remains purely theoretical, they capture the imagination and highlight the strange and counterintuitive nature of spacetime, according to Einstein's theory. Spacetime's everyday embrace, from satellites to our reality. While the bending of spacetime might seem like a concept confined to the realm of black holes and distant galaxies, its effects permeate our everyday lives in ways we often overlook. GPS navigation, reliant on precise timekeeping, would be impossible without accounting for the time dilation caused by spacetime curvature. Every time you use your smartphone to find directions, you're tapping into the profound implications of Einstein's theories. Moreover, the very understanding of our place in the universe has been irrevocably altered by Einstein's revelations. His work has reshaped our cosmic perspective. We no longer inhabit a static, unchanging cosmos, but rather a dynamic and evolving universe where space and time are inextricably linked, warped and woven together by the cosmic dance of mass and energy. This realization has profound implications for our understanding of reality. The legacy of Einstein's genius extends beyond the realm of physics. His revolutionary ideas have sparked countless scientific inquiries, technological advancements, and philosophical reflections. From the labs of scientists to the minds of philosophers, his influence is undeniable. The bending of space-time, once a radical concept, has become a fundamental pillar of our understanding of the universe, guiding our exploration of the cosmos and shaping our perception of reality itself. It is a cornerstone of modern physics. What does this invisible transformation make you ponder about the vastness above us? How does it change your view of the night sky? What other secrets of the universe might be unveiled as we delve deeper into the mysteries of space-time? The journey of discovery is just beginning.